All right, so we did some application problems with vectors, and this one was a little tricky to get started for a lot of folks. So I just want to show why it makes sense, the equation that was given, and how you could come up with that equation without being given it. So this is, oops, I drew that backwards because it's moving in. Here's Adrian at the coordinate of -3, comma 5, and this is the starting point, and the arrow, the vector, is going there because we're going towards the boat in the middle. So basically the story is Adrian and Lily are trying to converge on a certain boat. So Adrian is there, Lily is further over here at 7 comma 9, and Lily is rushing to help, like that. And Adrian has a speed of 4 meters per second, Lily has a speed of 6 meters per second. So the question is, yeah, Lily's a little farther away. Who's going to get there faster? So first thing that I want you to notice is that because they're moving directly in towards the boat that needs help, the angle theta stays constant the whole time. They're moving in. And what that means is that at any time you can draw a little right triangle, and that little right triangle is similar to the large right triangle. And so when you look at the larger right triangle, it has, I'll draw it here separately. The larger right triangle has a y coordinate of 5, an x coordinate of 3, and here's theta. And the little baby right triangle also has an angle of theta, but we don't know the x and the y coordinates of it. And that's actually what we're trying to do, is write an equation that represents what the x and y coordinates are at any time. And so what we use is similarity, and we know that the length of the hypotenuse is 4t, because that's the speed of Adrian. And so what we can do is set up a similar triangle here. The the bigger triangle has a hypotenuse of the square root of 5 squared plus 3 squared. So the large triangle has a hypotenuse of 34, and I can use cosine of theta to represent the adjacent side divided by the hypotenuse. But remember that we also have our little baby triangle, and I can use cosine of theta there to represent the x coordinate at a certain time t divided by 4t, because it's traveling 4 meters per second. So the smaller hypotenuse grows 4 times t. Now, because that theta is constant, you can set those two expressions equal to each other and get 3 over root 34 equals the x component over 4t. And if you cross multiply, you get 12t over the square root of 34. That's the x component. Similarly, with the using sine instead of cosine, we would end up with 5 over root 34 equals the y sub t over 4t. And the only difference here is that Adrian is moving down and to the right. And so one of our things should be negative here. We can put the negative over here on the 5, or you can put the negative on the y of t. Just keep in mind what direction we're moving in. Cross multiplying again gives me then negative 20t over root 34 equals y of t. And I want you to notice that these two components line up with what was given us right there. The I and the J are just the unit vectors that move in the x direction and the y direction, respectively. Now, the only other thing to account for are the 3 and the 5, and those are our initial coordinates. And just keep in mind that in the problem, they said the initial coordinates were given in kilometers, and so the x value of -3 becomes -3,000, and the y value of 5 becomes 5,000. So you can do exactly the same analysis with Lily, and you would get the other equation that's given. So I hope that makes sense for why those are the locations of the boats after t seconds. So what I'm going to do now is clear my screen and look at part B. Determine at which boat will arrive first and how much longer it will take the other boat to reach the boat in need. So I'll just do this again for starting out with Adrian, and then I guess because we're comparing, I should do both of them. So what we want to do is find out when they reach the origin. And so what we're going to do is take the x coordinate, negative 3,000, plus 12 over 34t, and set that equal to 0. And we should get the exact same answer as taking the y coordinate and setting it equal to 0, because it's moving directly to the origin. So it's not like the x coordinate should reach 0 earlier and the y coordinate should reach it later. They should come out to be the same value. If you move it over, I'll solve the top one. If you move the 3,000 over, then what you get is t equals 3,000 divided by 12 times the square root of 34. I'm going to pause for a second here. Okay, and so this will pop out to be the time that Adrian or Adrienne reaches the boat in need. And as a good double check, you should see that 5,000 divided by 20 times the square root of 34 should come out to be the same thing. And so let's see, does it come out to be anything nice? I don't know. 3,000 divided by 12 is 250, and multiply that by the square root of 34, and we get approximately 1457.74. Now let's do the same game with Lily's coordinates. I'm just going to do it for one of them at this time. So Lily would just be 7,000 minus 42 over root 130 t equals 0. So t equals 7,000 divided by 42 times the square root of 130. And let's see what that pops out to be. 7,000 divided by 42, square root of 130. This comes out to be 1,900, so approximately 1,900.29. So it looks like Adrian is going to get there first. And if we just subtract those two numbers, we'd figure out how much longer it takes for the other boat to get there. So about 450, maybe 443 or something like that. So that's the idea, modeling the movement of the two boats using vectors. Thanks.